our explicit form for geometric. Geometric is exponential at its heart. It's multiplying the same number over and over and over again. So our geometric explicit is going to be a sub n equals our first term times r to the n minus 1 power. All right, our recursive is going to be our first, that's live seat. You have to sit over there. That's what Hope said. It's okay, you can sit there. Hope is just disappointed in. All right, our recursive is going to be, our first term is some number, and every term after that is going to be a sub n equals basically the term before it multiplied by r. So we're going to have r times a sub n minus 1. That is the term before it multiplied by r gets me the term I want. For arithmetic, our explicit is, at its heart, just adding a number over and over and over. So our explicit is just going to be a little more complicated. It's going to be your first term plus your common difference times n minus 1. Your recursive is going to be, you have to have a first term, and you're going to take that first term, so we have a sub n equals whatever term you're looking for, you have to add the common difference to. So that's going to be a sub n minus 1 plus d. All right, we're going to get on to the fundamental counting theorem, and I'm going to kind of push through so we can get done on time. Consider it's 6 a.m., you're groggy, but you have to pick out an outfit to wear. Lucky for you, you did not do laundry, and you only have 3 pairs of pants, 3 t-shirts to choose from. How many outfits could you wear? We're going to say that you picked up one of your pair of pants and they smelled, so you're not going to wear them. We're only going to say 2 pairs of pants, just to speed things up. So you only have 2 pairs of pants. How many outfits can you possibly wear? What we're going to do to show this one is we're actually going to do a tree diagram, where we have you standing here, picking out clothes. That's you. You can tell because it's a stick figure, and you're all stick figures. All right, the first thing you're going to do is you're going to pick out what pair of pants you're going to wear. It is that hypothetical thing that we're going to assume that you could pick either pair, and we're going to go down both branches. So let's go down this branch. First of all, you pick out your pants number 1. You have 2 pairs of pants. You picked out the first pair, your red pair. I don't know. All right, after you pick out your first pair of pants, that means you have 3 options. You can either wear your shirt number 1. You could wear your shirt number 2. And finally, you could wear your shirt number 3. So with pants number 1, you have 3 shirts you can wear it with. There are 3 different outfits that you could put together with pants number 1. Now let's go back in time and say, I didn't like pants number 1. I didn't like any of those choices. I'm going to go back and I'm going to put on pants number 2. They're way cuter or whatever. All right, for pants number 2, we still have all 3 shirts we can pick from. So with pants number 2, you could wear a shirt. We're going to assume everything matches. We could wear shirt number 1. We could wear shirt number 2. And we could wear shirt number 3. So we can actually wear 1, 2, 3, 4, 5, 6 different outfits. There are 6 different outfits we could wear. So how many outfits can we have? We can have 6 outfits. But it's not always feasible to do a tree diagram every single time, especially when you have like 100 items to choose from. So we're going to lead into something called the fundamental counting theorem. That's what's right here. So what we actually just did is something called the fundamental counting theorem. We just did it in a tree diagram form. The fundamental counting theorem. The fundamental counting theorem is based upon the fact that you have several different groups you're choosing from, and you're choosing one item from every group. So with our outfits, we had a group of pants and we had a group of shirts. We had to pick one from each group. So it says if you could choose one item from group M and you can choose one item from group N, then the total number of 2-item choices is M times N. So if we came back here, we had the choice of 2 pants times 3 shirts would give me 6 total outfits. And so anytime we have a whole bunch of groups and we're choosing one from each, we can just multiply our total choices and we would get how many outfits or how many things we possibly have. And that's going to lead us to our first problem, and that is phone numbers. You all mostly have a phone that has a number attached to it, otherwise it's just a brick. So you have a phone number composed of 10 digits, not including your US code of 1. The first 3 numbers are known as your area code. Your area code cannot start with a 1 or a 0. That is true. Then your other 7 numbers are called your local telephone number. Those can also not start with a 0. You can have zeros in it, but you can't have it start with a 0. These are all real rules with phone numbers. Then it says how many possible phone numbers are there actually. This is a whole bunch of groups where I'm choosing one from each group. So if we look at a number, I'm just going to put it as blanks. So we have an area code, and then we have our local code, and that's a phone number. The very first number that we're going to have here is just picking one number. You're picking one number out of a bunch of numbers you can choose from. The problem is you cannot use 1 or 0, because it says the first 3 are area code, which cannot start with a 1 or 0. So that means we can only choose from 2, 3, 4, 5, 6, 7, 8, 9. So there are 8 possible numbers I could have for my first number if I'm just randomly picking one. The other 2 numbers don't have restrictions, so that means it can be 0 through 9, which is actually 10 digits to choose from. Then we have 10 here as well. Our local number, it can't start with a 0, so that means we have 1 through 9, which means I have 9 choices. Everything else doesn't have a restriction on it. Now this is the fundamental counting theorem because I'm going to pick one number from each of these bins. That's what it's saying. If you can choose one from each of them, it falls into the fundamental counting theorem. So that means all you have to do is take out your calculator and multiply 8 times 10 times 10 times 9 times 10 times 10 times 10 times 10 times 10 times 10. So it does in fact fall into that fundamental counting theorem. So we're just multiplying all of these guys together. And it's something like 7 billion. I forget the rest. 200. Okay. So it's 7,200,000,000 possible numbers. So there are right now 7,200,000,000 possible phone numbers you could get. There are more restrictions. You can't have 911 anywhere in there, and there's a couple other restrictions, but we're not going to worry about that. We're just going to say there's about 7 billion phone numbers to choose from. Anyone know how many people on Earth?
Like 4.
Huh.
What if everyone has
What was that?
What if everyone has people? Yes.
Only 4 of us, there's 4 people.
Let me see. There's Fritz. There's Chris. That's about 4. Yeah. All right. So there is a possibility that we're going to run out of phone numbers.
Why did you say 4?
Okay.
4 billion.
Yes. Shh. Guys. Okay. So continuing on. That is the fundamental counting theorem, right, Fritz?
Right.
Okay. Now we're going to get into permutations. Permutations are slightly different. Permutations are when your group, your pool of candidates or whatever, gets smaller every single time you picked it. With shirts and pants, they were individual items. What pants I chose didn't affect how many shirts I have. What shirt I chose didn't affect how many pants I had. Permutations are slightly different. Permutations are going to be like this one. You are given a presentation and you are going to start your presentation with a joke. You have 4 jokes to choose from. You are going to tell all 4 jokes. You just have to decide which joke you're going to tell first, which joke you're going to tell second, which one you're going to tell third, and which one you're going to tell fourth. How many possible ways are there to tell these jokes in a particular order? So it's a lot like the counting principle in the fact that, well, on my first joke, joke number 1, when I start off, I have 4 jokes to choose from. I have 4 jokes to choose from. I'm going to choose one from those 4. However, when I get to my second joke, I no longer have 4 jokes to choose from. Gentlemen, you guys are pushing it. I can always change your seats. Real easy. All right, joke number 2. I no longer have 4 jokes to tell. I'm down to 3 because I'm not going to tell the same joke twice. So we're going to jump down to 3 jokes. Then for joke number 1, or joke number 3, I should say. I don't know, I got to 1. We're going to have 2 jokes left. And for joke number 4, I have to tell whatever joke I have left. Well, now that it's set up like this, it turns back into the normal counting principle. I choose 1 from here, 1 from here, 1 from here, 1 from here. So to get our total number of combinations, you're just going to multiply. That is our fundamental counting theorem. This is if I'm choosing 1 from each group. So that's 12 times 2 times 1 is 24 possible ways to tell those jokes. Bless you. And what this is something called a permutation. These are called a permutation. A permutation is an order arrangement of items that occur when no item is used more than once. Each joke can only be used once. And here's the most important part of a permutation. The order of the arrangement makes a difference. Order matters. You're going to hear me say that a lot. Order matters with a permutation. Tomorrow we're going to talk about combinations where order doesn't matter, but for permutations, order matters. What joke I tell first matters. It changes the whole speech if I tell a joke out of order. All right, permutation. This is how we write it. A permutation of n things taken r at a time. So what we had was 4 jokes, and I'm telling all 4 jokes. So in this case, we would have 4 things taken 4 times. If I was only going to tell 3 jokes, I would have 4 jokes where I would take only 3 of them. If I was only telling 2 jokes, it'd be 4, pick 2. If I was only telling 1 joke, it'd be 4, pick 1. So that's what this n and r are. And how we usually write it, we write it with a p. We go permutation is how many we have. Pick a certain number of them. 4 jokes, pick 4. And here's the formula for it. But there's an easy way to remember the formula rather than having n's and r's in order, and we'll talk about that in just a second. All right, you are a coach of a Little League baseball team where you have 13 players. You need to choose 9 players for a batting order. The order of a batting order matters. You have to know who's going to go first. You can't just pick 9 people and they all rush to the plate for the first one. So order definitely matters. Who's first, who's second, who's third, order matters. So it's permutation because order matters. You have 13 players. You need to choose 9, and it has to be in a specific order, so it is a permutation. So you are going to do P. You're going to do P where you have 13 players, and you are going to choose 9 of them. We have 13 players, and you are going to choose 9 of them. Make sure I have my thumbs. Okay. So your number is your n, and this is your r if you're one person that likes to do that. When I do permutations, what I look at is which number is bigger. That's going to go on top. Sometimes they're the same, at which point it doesn't matter which one you pick to go on top. So I'm always going to put the bigger one on top and put a factorial. Then on the bottom, you're going to take your bigger number minus your smaller one and put a factorial after it. So to figure out how many batting orders you can form, we're going to do 13 factorial all over 13 minus 9 factorial, which is going to be 4 factorial. You do have a factorial button on your calculator. I am not always going to let you use it. But if you hit your math button and you go over your probability, there is a factorial button. For those of us that have to plug it in our calculators by hand, remember there is a slight shortcut. Not so much on this one. It's only a slight shortcut because remember 13 factorial is 13 times 12 times 11 times ... all the way to 4 factorial. And that would be over 4 factorial. Let me go one further here. It'd be times 5 times 4 factorial. Your 4 factorials would cancel out. So if you're using a calculator just to save you a little time, you can stop at 5. So if you're doing 13 times 12 times 11 times 10 times 9, 8, 7, 6, 5, you stop at 5 and you should come up with the right answer. If you plug that in correctly in your calculator, you should come up with 259,459,200 possible ways you could have that lineup set. All right, and that's how you calculate a permutation. We have one more to do, and that is if 4 officers are to be elected from a group of 12. Now, more often than not, I'll specify more about that. But with these offices, the office matters. We're talking about president, vice president, secretary, treasurer. I don't know. Those are 4 positions that are whole. Does order matter? Liv, if you're running for president, are you okay getting secretary? Does order make a difference? Yeah. I'm not just going to pick 4 of you and plug you in. It matters whether you're president. So order matters. So that means it is a permutation. What position you give each person matters. So order matters. So it's a permutation. So we have a group of 12 people, and 4 people are going to be elected. So that means it's a permutation where we have a pool of 12, and we are picking 4 people. The formula for that is our bigger number, factorial, over our bigger minus smaller number, factorial, which would be 12 factorial over 8 factorial. Once again, we can reduce that size if you're doing it by hand. You'd have 12 times 11 times 10 times 9 times 8 factorial over 8 factorial. So by hand, you just have to do 12 times 11 times 10 times 9, which is very possible with just a scientific calculator. This would be the type of problem on your test I would say you cannot use like your graphing calculator on. You have to use the multiplication. You have to show me that you can do it by hand, because that one's definitely one you can just punch in. And you come up with 11,880. All right, that in a nutshell is permutation and the formula for it, and the fact that you just need to know order matters. That is your importance today, is order matters. You don't have to check it on this homework, but tomorrow's homework and everything else after, you're going to have to decide if order matters or doesn't matter, because it's going to change what formula you are going to use. All right. We even have 5 minutes left. Awesome. All right.